Hey everyone, this is Unit 2, Periodic Table and Trends, Section 2, focusing in on the trends. This video is for Honors Chemistry, so if you're not in Honors Chemistry, then switch over to the other video. If you are, then we are on the right track. Let's go! First and foremost, we have a lot to cover in this video, so I apologize if it gets a little long, but I will try to be quick. Periodic table, just to review, organized from left to right by atomic number. We call the vertical columns our groups. Those have elements with similar properties, and we've looked at those groups already. Horizontal rows are called periods, and as you move across periods, we have different trends that develop as you move across the periodic table. So let's start talking about them. The first trend is nuclear charge. So I would probably organize your notebook or your notes so that you have a place to identify the trend, maybe highlight the name of the trend, and then put all the information underneath it, and then for the next one, go from there, okay? But this is one of the parent trends, if you will. So one of the major trends that really explains all the other trends. So have stars beside this one, okay? So I'm putting little stars beside this one so that we know that this one really should stand out amongst the others. So the idea of nuclear charge really is charge of the nucleus. The charge of the nucleus is positive because the nucleus has only protons in it, and so, well, protons and neutrons. Neutrons have no charge, protons are positive, so the nucleus itself is positive. This is really what holds the electrons into the energy levels that they're in. They're pulled in by the positively charged nucleus. The more protons I have, the more of a nuclear charge I'm going to have. So beryllium has 4 protons, so it has a nuclear charge of 4+, essentially. Oxygen has 8 protons, so it has a nuclear charge of 8+. That means that oxygen's nucleus is going to be pulling stronger on its electrons because they are pulling in harder, okay, or it's more positive, so it becomes able to hold in stronger. Basic trend, of course, is that if you're in a group or a vertical column, nope, this is a typo. That's a typo, sorry. So if I'm in a group and I'm going from top to bottom, so this should be groups right here, nuclear charge is increasing. If I'm going left and right across a group, nuclear charge is also increasing. So just within a period, as I move across, the atomic number goes up. So atomic number increases, therefore the number of protons increases, therefore the nuclear charge increases. As I move down, same thing, higher nuclear charge because of more protons. Now, shielding is an interesting thing. Shielding is another one of the parent trends, so put stars beside it. These are, nuclear charge and shielding are the two trends that explain all the other trends. So nuclear charge, the more protons there are, the more positive the nucleus is, the more it's going to pull on its electrons. Shielding is referring to the actual energy levels. The more energy levels something has, then the more shielding it has and the less pull the nuclear charge is going to have on the external electrons. So the energy levels act essentially like walls. They block the nuclear charge from the valence electrons. So the more walls I have between my nucleus and my valence electrons, then the more that charge is essentially going to be canceled out as you move out. If there's only one energy level, those valence electrons are held really strong by the nuclear charge. If there's 4 or 5 or 6 energy levels, then it's going to be harder for the valence electrons to actually be attracted to the nucleus because the nucleus is going to be essentially, the charge of the nucleus is blocked by all of those shields or walls. So again, I had a minor typo. I realized it's not really a typo, it just was, I was thinking about it a slightly different way. I was thinking about moving across the groups, but I like to think of it this way now. I want to say it this way. So within a period, if I'm moving left to right, shielding stays constant because I'm not adding any more energy levels. Remember, as we move across, we have our 3rd energy level. It stays in the 3rd energy level. This is all the 2nd energy level. This is all the 6th energy level with the 5D, but 6 is still there, whatever. So we're not adding any more energy levels, so we're not adding any more shielding. As I move down, though, each line represents an energy level 1, 2, 3, 4, 5, 6, and 7. So the further I move down within a group, the more energy levels there are, the more shielding there is, okay? So as I move down, this helps explain why we already talked about previously that francium is the most reactive metal, because within the alkali metals, they all have that one electron they want to get rid of. They all form a 1+ charge. But francium's the most reactive because it has the most shielding. There are more energy levels blocking the nuclear charge from its valence electrons, so it's very easy for francium to get rid of its valence electrons because the nucleus is barely holding on to them as is. There's so much shielding that it's blocking it out. Okay, so shielding as a trend is referring to whether or not, or how much, the extent to which the nucleus's charge is being blocked from the valence electrons. So y'all knew it wasn't all that perfectly easy, because the nucleus is pulling in. So these blue arrows are the attraction of the nuclear charge, right? And the red arrows are kind of referring to the shielding. They're referring to the cancellation, if you will, of the charge of the nucleus because of the repulsion of the internal electrons. So when you take nuclear charge and combine it with the understanding of shielding, you get what's referred to as the effective nuclear charge. Okay, effective nuclear charge is abbreviated with the symbol Z and then a suffix EFF. That is completely unreadable. Let's get a different color. A Z and then the subscript EFF for effective. Okay, so ZEF essentially. When I talk about it in class, I'll say ZEF or ZEFF, whatever. But effective nuclear charge is basically referring to the exact positive charge that's experienced by the valence electrons. So the nuclear charge minus the shielding gives us our effective nuclear charge. So that's exactly what we're going to do. When we calculate effective nuclear charge, we're going to look at the nuclear charge, so the total number of protons. We're going to subtract the number of electrons that exist that aren't valence electrons, and that gives us our essential effective nuclear charge. Let's look at an example. All right, so for phosphorus has 15 protons, so it has a charge of 15 for its nuclear charge. So when we're calculating, that's what we put it in as. Then we take the total number of electrons, which traditionally should be 15 for a phosphorus atom, and subtract its valence electrons. It has 5 valence electrons. Okay, so that means that we know it has 5 valence electrons because it's in group 15, and so everything in group 15 has 5 valence electrons. So that tells us that we have 10 internal electrons. So essentially we take the protons, subtract the 10 internal electrons, and that gives us the overall effective nuclear charge. So for this one, the ZEF is positive 5. All right, now we get into the more specific trends. First one is atomic radius. So atomic radius is half the distance from the nucleus of one atom to the nucleus of another identical atom bonded. That's kind of ridiculous. Essentially, I'm referring to the fact that if we have a circle and you have a center point and a diameter, half of that is the radius. Let's just go with that, okay? The definition up here is an important definition to know, that it is measured by looking at two atoms that are identical and putting them together. Basically, what that does is it takes the average of their radii, because, you know, certain atoms could stretch out larger. If it becomes an ion, it changes, so that gets a little questionable. But essentially, atomic radius is the radius of the atom, okay? If something has a high effective nuclear charge, it has a small radius. Why? Because as the nucleus pulls on the electrons, the stronger the nucleus gets, the stronger it's pulling in on its outer electrons, and so it's going to cause the atom to be a little bit smaller. All right, so the basic trend for atomic radius is that within the groups, as I move from left to right, atomic radius decreases. So the smallest atoms are found are on the right-hand side of the periodic table. The largest are on the left-hand side of the periodic table. And then due to shielding, the more shielding there is, the less pull the effective nuclear charge is going to have on those external electrons, external electrons. So as I move down and I have more and more shielding, I'm going to have larger atoms, okay? So the trend is as I move left and down, I have the largest atom. So the largest atom on the periodic table is francium. That is a very large atom. The smallest atoms on the periodic table would be found in the top left corner. Again, due to increase in nuclear charge as I move across a period, I'm going to be pulling in harder on the external electrons, so it becomes a smaller atom. And due to shielding, as I move down, it blocks that charge that would be there to pull in. It blocks that charge, so it makes it so that they are larger as you move down. Now, ions are a little unique. As I lose valence electrons in a cation, I lose a whole energy level, right? Because a lithium that has one valence electron, when it loses that valence electron, it exposes the energy level below it. So essentially, it's getting rid of that whole energy level on the outside, and you're left with a smaller atom. So cations are always going to be a little bit smaller than the atom that they came from. Anions gain electrons, so they add electrons into an energy level that wasn't there before. So that causes the atom to become larger once it gains that electron. So cations are always going to be smaller than their parent. Anions are going to be larger than their parents. This chart just shows the comparison between atoms and their ions. So over on the left-hand side, we have groups 1, 2, and 3, looking to see that the parent atom is larger. The parent atom is green. The ion is smaller because we've lost those electrons. So we've lost an energy level, so we've created a smaller ion. On the right-hand side of the table, in groups 15, 16, and 17, we see that when we add electrons, we add an extra energy level, so the radius gets larger. Okay, so the next trend we're going to look over is first ionization energy. First means first, of course. Let's break the rest of this down. Ionization means become ion. Okay, so to become an ion. And energy, of course, is the energy required to do whatever it is that you're referring to. Okay, so first ionization energy. Ionization energy is the energy required to remove a valence electron. Okay, so remove a valence electron means the energy required to make it into a cation. Well, we already know that some elements on the periodic table, referred to as metals, very easily form cations. Non-metals form anions, usually. So they want to gain extra electrons. So you can already probably predict what the trend is going to be like. Metals are going to have very, very low ionization energy because they want to get rid of those electrons. They want to get rid of those valence electrons. It's easier for them to get to 0 valence electrons and release the next energy level than it would be for the metal to actually gain all the electrons it needs to fill that outer energy level. So when we're looking at first ionization energy, we're referring to how much energy it takes to actually form a cation. Cation, okay? So we show a little reaction to show this, and that's this reaction right here. This is something that especially those of you going into AP and IB and chemistry in the future, this is something you'll see a lot. The X is referring to just a generic element. It is in the gaseous state. Gaseous state is always going to be the highest general energy state for a substance prior to ionization or prior to plasmalizing. When something's a gas, it's possessing the most energy it can without falling apart, essentially. When something is falling apart, quote unquote, that means it's ionizing. So this equation is showing element X, or any element in its gaseous state, to form a cation and release an electron. That's the equation that we use to essentially refer to that. And that would also include a large amount, or perhaps a small amount of energy. Okay, it just depends on the element itself. Ionization energy is going to increase as effective nuclear charge increases. So as I move right across a period, I'm going to increase my ionization energy. Now think about that. Piece it together because you have all the stuff to piece it together. We know that as I move right across the periodic table, the number of valence electrons goes up. So the closer I am to 8 valence electrons, I don't want to lose electrons. I want to gain electrons. So obviously, it's going to take a lot of freaking energy to force me, being that I already want more electrons, to get rid of the one I already have. That's insane. If I'm fluorine or chlorine or something like that on that side of the periodic table, I want an extra electron. Why would I ever want to lose an electron? So that atom is going to take a ton of energy to force it to lose an electron when it's already trying to gain electrons to get to 8. Okay. Second ionization energy, second ionization energy, and third ionization energy, and fourth, etc., are going to be even higher. So if I did force chlorine to remove an electron, it's going to be a really high energy. If I try to get it to remove a second, it's going to be an enormous amount of energy. So the more electrons I try to remove from a nonmetal, the more energy it's going to take. Elements like metals that are close, that only have 1 or 2 or maybe 3, it's not going to take as much energy to remove those 1, 2, or 3 because the atom already is interested in losing them to expose its next layer. But as I move across to the right, it's going to go up. So here's your trend for ionization energy. The highest ionization energies are going to be found over here. And we do include the noble gases in this trend because at this point, a noble gas has 8 valence electrons. You better believe it's going to be difficult to get that noble gas to get rid of one of its electrons and form a cation. It ain't going to happen. So that amount of energy is going to be enormous in that last column. So in general, fluorine, helium, neon have the highest ionization energies. Things over here in the alkali metals, they don't give a crap about that electron. It doesn't take any energy for them to do that. They're like, sure, go for it, take it. I don't care. So it takes very little energy to actually get them to lose their electrons. Okay, so it's not very difficult to actually do that. And the less shielding. So like francium, the less shielding, or excuse me, the more shielding it has, the less nuclear charge, the more prone it is to get rid of that electron. So francium has the lowest ionization energy because it has a pretty high charge on its nucleus, but it has the most shielding. So that nucleus is not able to hold on to its valence electrons as well as it should. So francium is like, meh, who cares? Take the electrons. The last trend is electronegativity. So while ionization energy is the energy it takes to make it into a cation, the electronegativity is essentially how likely it is to form an anion. So electronegativity is basically saying how attracted to electrons is this substance. So we already know that the halogens with their 7 valence electrons look like that. Okay, because they want that last electron so freaking bad that they are willing to do anything to get that last electron to make a total of 8. Okay, so electronegativity is referring to essentially forming an anion. Okay, so if I am very prone and very apt and very likely to form an anion, I'm going to have a very high electronegativity. So a high electronegativity means that I have a very, very strong ability to pull on the electrons. So you can probably expect that since everything over here forms positive, you can't even see that, forms positive ions and these form negative ions, the highest electronegativities are going to be over here, okay? Excluding this group. We know that they form a charge of 0. That means that they want no electrons. They don't want to get rid of any, so they have super high ionization energies, and they don't want any more. Why would they want any more? Who cares? They don't want to have 9. That's weird. They want 8. So they have no interest in no interest in electrons. So they have an electronegativity in that column of 0. Okay. All right. What I want you to do for your review on this or your summary, I want you to make a little chart that organizes the trends and helps you to understand a little bit more about that. Okay. If you've watched this far in the video, you should know that next class you have a quiz on this section of notes. Good luck. See you then. Bye.